Page 5, limiting reactants and some stoichiometry. Nice one about this one. Well, nice from a teacher standpoint is you have to write this reaction, and so if you don't do it correctly, you're not going to get the right answer. 35.1 grams of aluminum is reacted with 42.9 grams of iron 3 oxide. Let me just double check. Iron is a +3 charge in this case because of that. Oxygen, it's Fe2O3. The products will be aluminum oxide. Al has a +3. Oxygen is a -2. Same crisscross, Al2O3. And you're also going to get iron, metal, a single replacement reaction. Nice thing is it's already balanced, so we're good there. What mass of iron will be produced if we have a 35.1? So this BCA table, I'm cutting to the chase. They tell me how much aluminum I'm going to start with, but I'm going to have to convert it to grams, or from grams to moles. They are, let me go back. They also tell me how much iron 3 oxide. And what they're really asking me about is how much iron will be produced. The box down here is going to be an important one. I'm not really going to care about this. So this is one of them types where, well, they're giving you two, I don't know, it's kind of like we had 6 hamburger patties, 3 buns, 7 pieces of cheese. How many hamburgers can we make? There's going to be something that holds us back. So we have 2 ingredients, 2 reactants, and we're going to have to figure out which one is the limiting reactant. So the first thing we need to do is convert their grams to moles. 1 mole of aluminum is about 29 grams. There's aluminum. 27 grams. When I get all done with that, that's going to be about 1.3 moles. I'm going to write 1.3 moles there. The other substance I'm starting with is iron 3 oxide, and I have 42.9 grams of Fe2O3. I got to add up 2 irons and 3 oxygens, and I'm going to get 159.7 grams per 1 mole of that stuff. So that's only a 0.27 moles. Let's check the recipe though. The way I like to do this is what I'm after over here is iron. So I'm going to draw a box. I have enough aluminum, 1.3 moles. Well, let's see. The nice thing, this is an easy one. It's a 1 to 1 to 1 to 1 ratio. For every 1 mole of aluminum, I'll get 1 mole of iron. Well, I got 1.3 moles of aluminum, so I have enough for 1.3 moles of iron. But I only have 0.27 moles of iron 3 oxide, so I can only make 0.27 moles. That's the smaller number. That's all I can get. I'm going to cross off that number. I'm not getting 1.3 moles. I only have enough for 0.27. If I can make 0.27 moles of iron, I can use that to figure out, well, let me just kind of look. Why did I cross off this? Because I have enough aluminum for that much, but I'm not using that much. My limiting reagent then is Fe2O3. I only have enough of this stuff to make 0.27 moles, so I did that wrong. Early in the morning. My limiting reagent is Fe2O3. I'm going to have excess aluminum, 1.3 moles of aluminum. All I have to do is write aluminum. That's the excess. So, next step. How much can I make? Theoretical yield, 0.27 moles. But I'm going to want that in mass of iron. So I could do it here, 0.27 moles times, how much does 1 mole of iron weigh? Check the periodic table. Iron is 55.85. So if I multiply that by 55.85 grams, I'm going to get 15 grams of Fe. Let me just double check that. 0.27 times 55.85 equals about 15.1. Okay, Now the next part. So how much extra stuff am I going to have? I'm going to get rid of this. Maybe bad planning. You see, I know that I can only make 0.27 moles. I'll use up all of this. There'll be none left because that was the limiting reagent. But how much aluminum will I have? Well, 1 mole of iron required 1 mole of aluminum. Well, I'm only making 0.27 moles of iron, so I can only use up 0.27 moles of aluminum. 1.3 minus 0.27 is 1.03 moles. If I had 1.03 moles of aluminum, but I'm pretty sure it says what is the mass of excess reagent, and 1 mole of aluminum is 26.98 or 27 grams, I'm going to have an extra mass of 27.8 grams of aluminum. There's one of my answers, another answer, another answer, and another answer. Next one, less complicated, but we have to pick out the information. There was a lab that was going on. This lab had to do with, well, let's see, it must have had something to do with nickel, must have had something to do with silver, but hopefully they'll tell us the whole thing because we're going to have to write a balanced equation. Let's see, a piece of nickel, that would simply be Ni, in silver nitrate, AgNO3, Ag is always +1, NO3 is -1. It's a single replacement, so it kicks out the silver, it's precipitated, and when we're all done, we'll have nickel 2 nitrate, NiNO3 taken twice because nickel has a +2 charge. Is that balanced? I don't think so. If I see 2 nitrates over there, I'm going to need 2 nitrates over there. But now that I did that, it's gave me 2 silvers, so now I have 2 silvers. I now have the balanced reaction. Next step is to figure out how much. They didn't just tell me, but it's simple subtractions from the mass of nickel reacted. Well, they told me they had a 5.25 gram chunk of nickel, and I'm going to subtract, when they're all done, it's 4.89 grams of nickel. So how much disappeared or got used or got consumed? Looks like 0.36 grams of nickel. Anytime we're trying to do BCA type stuff, though, we're going to have to, we need moles. So 1 mole of nickel, according to the periodic table, is 58.7 grams of nickel. So that's 0.006 moles of nickel. I didn't really save myself much room for a BCA table, but I think I can fit it in underneath there. What do I know? Nickel. What do I want to know? Looks like silver. So the only 2 important boxes are going to be, actually there's 0 to begin with. Those are the only 2 important boxes. How much nickel did I start with? 0.006 moles. Check the recipe. 1 mole of this will make 2 moles of that. It's a 2 to 1 ratio. So 0.006 moles of nickel times 2 moles comes from 1 mole equals 0.012 moles. So theoretically, I put this, let's see, let me draw the path. Once I got my moles of nickel, I put that there. I use that to find there. Now I got to come back down here and convert that back into grams for a theoretical yield. The theoretical yield should be in grams. 0.012 moles of Ag, silver, and 1 mole of silver is 107.87. 107.87 grams of silver. And I should get, multiplying that out, I should get 1.32 grams of silver. That is theoretically the maximum that we can get based on how much disappeared. Well, somebody went there, they got their beaker, they dried it out, and here's some data. And I can use that to figure out how much they actually got. Actual yield will be 103.15 grams. That's the mass of both the silver and the beaker. Subtract the weight of the empty beaker, and I'm going to get 1.08 grams of silver. Is that what I was supposed to get? I was supposed to get 1.3 grams. What is my percent yield? Actual divided by theoretical times 100 to change it to a percent. So if if those people in the lab got 1.08 grams out of the 1.32 grams that they were supposed to, that would be an 82% yield. And finally, just some introductory stuff, a little bit about the acids and bases and what's stronger and what's weaker. We know that this scale stretches from 0 or 1, I don't care, all the way up to 14. We know that in the middle is 7. This section down here are well, I suppose it should go right to there, right up to 7, because 7's neutral. This section up there is the acids. This section down here is the bases. And then as you go from 7 to 14, as far as a base goes, it gets to be an increasing strength. That totally makes sense. You get a stronger base as the numbers get higher. But the interesting thing is, and hopefully you remember this, as you go down, the lower the number, you also get an increasing strength. So starting at 7 and going off to the edges, it gets stronger. A stronger acid as we go left, a stronger base as we go right.